In this section, we'll break down the transformer attention mechanism in a way that's useful for LLM and AI engineer interviews. We'll cover what attention is doing conceptually, how the core math works with queries, keys, and values, how it's implemented in code, and how to turn that understanding into a strong portfolio signal. The goal is not just to memorize attention, but to explain it clearly and apply it confidently. Attention is such a common interview topic because it sits at the heart of transformers. Unlike RNNs or CNNs, transformers move information across a sequence through attention, not step-by-step recurrence. That makes it a great litmus test. Interviewers can quickly tell who truly understands how LLMs work versus who has only used them. Strong candidates can explain attention at 3 levels: the core idea, the math, and how to implement it. Here's the roadmap for this section. We'll start with the core attention operation, what queries, keys, and values are actually doing. Then, we'll look at the scaled dot product equation behind the mechanism. After that, we'll cover multi-head attention and why multiple heads matter. We'll also touch on masking, including causal masks and self versus cross attention. Finally, we'll close with portfolio and career strategies that help demonstrate real engineering fluency. Attention really comes down to one simple pattern. First, we compare queries to keys to measure relevance. Then we turn those scores into weights, so the most important matches stand out. Finally, we use those weights to mix the values and produce the output. Whether it's self-attention, cross-attention, or multi-head attention, they're all just variations of this same 3-step process. Self-attention starts with 3 inputs: query, key, and value. The query is what a token uses to ask, what other context do I need? The key is how each token describes itself, like a label saying what it represents. And the value is the actual information passed along if that token is relevant. In self-attention, all 3, Q, K, and V, are created from the same input sequence. This slide shows the scaled dot product attention equation. First, we score each query against the keys using a dot product. Then we divide by the square root of dx and k to normalize those scores, keeping them from getting too large as the vector size grows. That matters because oversized scores can make softmax saturate, which weakens learning by shrinking gradients. Finally, the resulting attention weights are used to mix the values. Here's why scaling matters in attention. As the key dimension grows, dot products naturally get larger, roughly proportional to the square root of DIROK. If we feed those large scores directly into softmax, it becomes too peaked, and the gradients get very small. So we divide by the square root of DIROK. That keeps the scores in a stable range, makes softmax more informative, and helps training learn effectively. Self-attention lets tokens watch one another. Here, the queries, keys, and values all come from the same input sequence, so each token can compare itself with every other token and gather relevant context. That means a word's representation is no longer fixed. For example, the word bank doesn't always mean the same thing. After self-attention, its vector reflects whether the sentence is talking about a riverbank or a financial bank. Multi-head attention means the model runs several attention operations in parallel, each with its own learned projections. That lets different heads focus on different kinds of relationships, like syntax, coreference, or positional patterns. The key idea isn't that every head is always cleanly interpretable. More safely, multiple heads give the model more expressive capacity than a single attention head, helping it capture a wider range of patterns at the same time. This slide maps the 3 attention patterns in an encoder-decoder transformer. In encoder self-attention, input tokens attend to each other to build contextual representations. In decoder self-attention, a causal mask limits each position to earlier tokens. So, generation stays autoregressive. Then, Cross-attention lets the decoder query the encoder's outputs through key-value pairs. Being clear on where each type lives and why is a strong interview signal, because self-attention and cross-attention are often confused. This slide compares self-attention and cross-attention. In self-attention, the query's keys and values all come from the same sequence, which helps the model build contextual representations. That's used in encoder layers and also in the decoder, where causal masking prevents looking ahead. Cross-attention is used only in the decoder. Queries come from the decoder, while keys and values come from the encoder output, letting the model connect the input sequence to the generated output. Masking controls what information the model is allowed to use during attention. A causal mask prevents the decoder from seeing future tokens, which is essential for autoregressive generation. A key padding mask hides padded positions in a batch, so those filler tokens don't affect the attention scores. And a custom attention mask can block selected query key pairs, enabling more structured or sparse attention patterns when needed. Here's causal masking in plain terms. At position I, the model can only look at tokens up to I, never ahead. We enforce that by setting future positions to negative infinity before the softmax, which makes their attention weight effectively 0. In PyTorch, this usually shows up through add-a-mast in NN, multi-head-attention, and getting the mask shape wrong is a very common real-world bug. In PyTorch, the main attention APIs to know are NN, multi-head-attention, and scaled, NumPy, product attention. Multi-head-attention is the high-level module, and if you set need weights to false, it can use the optimized SDPA path for faster inference. Scaled, DOIT product attention, is the core functional kernel and is already used inside multi-head attention and transformer encoder layer. Also, be clear on the key parameters. Embed dim, numHates, ATN mask, and key panning mask, since each one changes how attention behaves. Attention isn't just a math concept. It's a performance-critical kernel. In production, what matters is understanding how the framework actually executes it. In PyTorch, scaled product attention can take optimized fast paths, but only when the right conditions are met. Even something like setting need weights to false can matter, and validating that across batch size, sequence length, and inference mode, that's the kind of hands-on benchmarking that shows real engineering fluency. Interview prep for attention usually happens at 3 levels. First is conceptual, why attention helps, what self-attention is, and how to explain it clearly without equations. Second is mathematical, understanding scaled product attention, including why we divide by square root of d's cum to k and apply softmax. Third is implementation, masks, tensor shapes, multiple heads, and translating the equation into PyTorch code, then debugging it when things go wrong. Here are 3 portfolio projects that show real fluency with attention. First, a compact transformer block. Build Q, K, and V from scratch. Apply masked scaled product attention. Compare the result to PyTorch and visualize the heat maps. Second, a self versus cross attention demo in a toy encoder-decoder setup with the differences clearly documented. Third, an attention benchmark that profiles multi-head attention across batch sizes, sequence lengths, and settings, then explains the performance results. Common interview misses on attention are being too vague, overclaiming what heads do, or skipping masking entirely. Don't just say attention helps the model focus. Name the equation and walk through scores, softmax normalization, and value mixing. Describe multi-head attention as parallel projections into different subspaces, not tidy human roles. And be ready to explain causal versus padding masks, including when they matter, and how shape mismatches show up in implementation. If you're building a career around modern AI systems, attention is a foundational competency. In a technical screen, You should be able to explain it clearly at the level of concept, math, and code. In a take-home project, show that you can implement it, profile it, and visualize how it behaves. In your portfolio and product conversations, highlight trade-offs, failure modes, and how attention shapes context, latency, and model limits. Here are the key takeaways on attention. The core mechanism is simple. Compute scores with QK transpose, scale by the square root of dk, apply softmax, and use those weights to mix the values. V. Self-attention builds context within one sequence, while cross-attention links the encoder and decoder. Multi-head attention runs this in parallel across subspaces, giving richer representations. For interviews, know the equation, code it, optimize it, and show a real example.